And the next speaker is going to be Tooba Bibi, and the title of her talk is Quantum Carpets, Efficiently Probing Fractional Revivals in Position-Dependent Math Systems. And from School of Natural Sciences from the National University of Science and Technology, Pakistan. So please go ahead, and questions will be collected in the Discord.
Okay, thank you, QWorld, to give me this opportunity to talk about this. So I will talk about efficiently probing fractional revivals in position-dependent math systems. These are the contents of my talk. First, I will develop some mathematical background, and then I will talk about quantum revivals and fractional revivals for position-dependent math systems. And I will talk about these structures with the help of two methods, which are probability density functions and information entropy density function. And at the end, I will compare the structures we have observed with the help of information entropy density with the structure that is obtained by autocorrelation function. And then I will conclude my talk. So here in the quantum world, there are lots of phenomena that do not have analogous approach in classical world. One of these phenomena is the observation of quantum revivals. When we study the quantum dynamics of well-localized wave packet, we see the non-classical feature, which is quantum revival and fractional revival. For the short interval of time, when we study the time evolution of well-localized wave packet, we observe that it follows the classical trajectory, but in a long time interval, we see that the localized wave packet starts spreading, and afterwards, after a spreadness, it again starts to reshape its original structure, and then again gets the original form. So when the point where the localized wave packet have a original shape and then spreadness and then again to going to its original shape, the time it requires is quantum revival time. So here I will talk about the structures of quantum revivals for position-dependent mass systems. And as position-dependent mass systems are typically the charge carriers moving in a crystal, and sometimes our system is anisotropic. In that case, the mass could be effective mass, which is different from the free state mass of a particle, and the mass starts it starts depending upon the position of the system. So here I will discuss the position dependent mass, the structure of revivals with the help of probability density function and information entropy density function. And we will explore these with the help of image plots known as quantum carpets. So developing the mathematical background behind it, as we know that classical Hamiltonians contain kinetic energy term and potential energy term, and these two terms are depending upon the momentum and position. When we, in case of position dependent mass, here the kinetic energy term is also depending upon both functions, momentum and position. So when we quantize this Hamiltonian, there is ordering ambiguity in this, as we know that position and momentum operators are non-commutable. So the approach we use here to write this kinetic energy in symmetric form is introduced by von Roos, and with the help of that we can write this kinetic energy term in this way. The position dependent mass system we are considering here is infinite potential well with the width of L, and the potential here is 0 inside the well. the spatially varying mass we are choosing here is this mx, where this m0 is the free state of mass and this tau is the strength parameter. Considering these boundary conditions of infinite potential well, and for this mass of the system we solve the Schrödinger equation, and we get the eigenstate function and eigenenergies of the system. With the help of these eigenfunctions and eigenenergy of the system, we can construct a wave packet for our system, and we can study the time evolution of that wave packet. Here in this slide, I've shown the wave packet. We can write the time dependent wave packet for position dependent mass system in terms of superposition of the eigenstates of our system we are choosing, and these are the eigenenergies of the system. This tau is showing that we are considering the position dependent mass, and when we take tau equal to 0, that will be the case when there will be the rest mass. So this Cn is the expansion coefficient, and we can find it with the help of initial wave packet and the eigenstate function of the system. For our convenience, we consider the initial wave packet, which is Gaussian, and with the help of this wave packet, we can write the time-dependent probability density in position space. With the help of this probability density function, we can study the time evolution of the wave packet. So in when the well-localized wave packet starts, we studied the quantum dynamics. We see that because of the several bouncing of the packet with the walls of potential well, there comes the multiple peaks, and then these multiple peaks also starts traveling with their own individual phases, and there are lots of constructive and destructive interference patterns occurs, and the original shape of wave packet collapse. But later at some time, again it starts to reshape, and original wave, we get the original wave packet, and at that time we say that it's the full revival, quantum revival, and the time it takes, we say that it's the quantum revival time. And during that time, there are also some fractional part of time where the partial reshaping of that wave packet occurs, and we say that these are the fractional time and fractional revival time. The time we can find the time that when the full revival or fractional time occur, we can get that with the help of this equation. And here we can see that quantum revival time is depending upon the eigenenergy states of the system. So it's the derivative of eigenenergy states of the system. For the first time we will get, that will be the classical time, and for the when the derivative will be 0, and for first derivative we will get the quantum revival time. So with the help of this equation, we have studied the probability density function at specific time. Here we consider the snapshot in first figure for 1/4 of quantum time revival, and second one is for half, and we have plotted for different strength parameters. For tau equal to 0, this one is the case when there is rest mass, while these are for other parameters. So we can see that as we increase the strength parameters value, the peaks of the probability density peaks are shifting towards the higher mass, and in other words, it is shifting towards the lower position. So in next slide, we have shown the previous one were for some specific time, but these ones are for our time interval. Here on left side, this quantum corporate is for constant mass, while the right side one is for the position dependent mass. In these corporates, the bright colors are showing the high probability density peaks, while the dark one is showing the low probability density peaks. And we can if we compare the both plots, we can see that for the position dependent mass system, symmetry is broken and the peaks are shifting towards the higher mass region. So we have studied this for the position space probability density. If we want to see these structure revivals for position dependent mass in alternative way, which is momentum space, then we can get the momentum space eigenfunctions with the help of Fourier transform. And again, we have plotted the probability density function in momentum space for different strength parameters, and we can plot the quantum corporates for momentum space. Here we can see the different designs for the same system, and we can also see that again in case of the position dependent mass, the symmetry has broken. So next, we have used another probe, which is information entropy density. As the information entropy density is related to the uncertainty, so if we have the lower uncertainty, and we will have the higher localized wave packet and higher accuracy. So we can relate the information entropy with the localization of wave packet, and we can study the dynamics of the wave packet with the help of information entropy density. We can write the information entropy density in this way in terms of probability density function. For momentum space, we can write like this, where Q will be obtained with the help of Fourier transform, and some of these entropies satisfy this relation. This relation is the alternative way of writing the Heisenberg uncertainty principle, but in information entropy density form, information entropy form. So next, we can write the information entropy density function in terms of this, and we have plotted for at some specific snapshots of different time, and we have shown in first figure the probability, the position space entropy density, and in next figure we have shown the momentum space entropy density for two different values of the strength parameter tau. And here the more conventional way to understand the structure revivals is autocorrelation function. In this figure, I have shown the comparison between these two process. Like the black one is showing the structure revivals which are obtained with the help of autocorrelation function, while the gray one is with the help of information entropy density. And we can see that the information entropy density is more efficient and more sensitive to identify the structure of fractional revivals. So if I conclude my talk, it is that we have studied the position dependent mass system structure effect of structure revivals on position dependent mass system, and we have seen that the quantum corporates can be served as efficient probe to not only identify the fractional revival, but also it is better probe to understand the effect of position position dependent mass on this phenomena. And with the help of these structure revivals, we can understand the quantum dynamics of the wave packet and decoherence of the wave packet. For further interest, I have shown some references to understand its applications. So thank you. These are the references of my talk.
Oh, great. Thank you very much for this talk. I don't see any comments here. Right. Maybe I would ask, how did you actually calculate these? How did you solve the equation? Was what method did you use?
Schrödinger wave equation.
Yes.
Well, we considered the some boundary conditions, and then later we used some substitution in that equation to make it simple, and then we solved.
So you have analytic. So do you have an analytic formula for all the?
Yes.
Oh, okay. I missed that one. Okay, that's very cool. Okay. Okay, there's a question. How do you program a quantum carpet? From Rafael Vasquez.
We can use different languages like Fortran or Python to program this one. We like put the equation in program and the conditions we want to use, and then for that we run it in Python. We can use Python and Fortran. I also tried in MATLAB too.
Okay, I hope that answers the question. And then with that, I thank you as well.